In this session, we're going to discuss counting. So, counting means we're going to determine the different ways in representing a pattern or in doing something. Okay? So, under this topic, we're going to discuss basic principles about counting, pigeonhole principle, permutation and combination, binomial coefficient and identities, and we're going to generalize permutation and combinations. So let's start with basics of counting. So under this topic, we're going to discuss product rule, sum rule, and subtraction rule, or we call it principle of inclusion and exclusion. So let's start with the product rule. So product rule means a procedure can be broken down into a sequence of two tasks. There are n sub 1 ways to do the first task and n sub 2 ways to do the second task. Then there are n sub 1 times n sub 2 ways to do the procedure. Okay, so basically, if you have two in a pattern, if you have two characters, okay, the first character we have different ways of representing it. It is your n sub 1. And the second character, the different ways will be represented by n sub 2. Multiply these two, that, that will be are and ways in representing that pattern. So that's the meaning of product rule. Okay. So for example, how many bit strings of length 7 are there? So we're going to determine the count, okay, of 7-bit strength, the number of distinct 7-bit strength. Okay. And we all know that in a bit, you could only represent it using 0 or 1. So it means in one position, in a 7-bit length, we have two ways to represent one position. Okay, so it means, so 7 position, so it means we're going to multiply 2 times 2 times 2 times 2 times 2 times 2, okay, times 2 to get the number of ways in representing 7-bit string, okay? Or it could be represented by 2 raised to 7, and the result is 128. So it means we have 128 distinct, okay, characters or 128 distinct value that could be represent a 7-bit length string. Okay, so that's an example of a product rule. Here we just only have one task. So let's increase the number of tasks. So another example. How many different license plates can be made if each plate contains a sequence of 3 uppercase English letters followed by 3 digits? So we have 6 positions. Okay, the first 3 positions will be allocated for 3 uppercase English letter, and then the next 3 will be for the 3 digits. Okay, for the English letter, how many alphabets do we have in an English? Okay, in an English alphabet, we have 26. So it means we have 26 ways in representing one position for the first 3 position. And for the last 3 position, how many integers do we have? 0 to 9, so we have 10. So it means we have 10 ways in representing the last 3 digits or last 3 positions of the plate. Okay, so to get all possible plates, okay, so we're just going to multiply 26, 26, 26, multiply by 10, 10, and another 10. Okay, so again, why 26? 26 characters for the first position, 26 characters for the second, 26 for the third. And for the next 3 position, we have 10 for the integer, 10, 10. Multiply, we have this, 17,576,000. Okay, so that's the number of different possible license plates. that you could generate based on 3 uppercase English letter and 3 digits. Okay, so let's discuss the counting function. So basically, it's just generalize our um, our product rule. Okay, so how many functions are there from a set with m elements, which is your domain, to a set with n elements? So basically, we're just going to multiply the number of elements of the result. Okay, so for example, okay, n times n times n times n. So this is the result. Okay, and equals to n raised to m, wherein m is the number of elements. Okay, or the number of elements or a number of position of the domain. Okay, so which is the same as with the R product rule here. Okay, and in case we have this rule, we have one-to-one function. If say one-to-one function, one input will result to an exclusive result, which is not shared to other, okay, to other values in your domain. Okay, so how many one-to-one functions are there from a set with m elements to 1 with n elements? So let's suppose we have 3 position. So the first position, all elements could be used to represent the first position. So it means it is your n or m. Okay, and then second, since you already use one of the elements of the domain, you're going to subtract 1 from the number of elements. So the second position will have n minus 1. So it will be, okay, so you're going to have subtract 1 element from the given set for the second position. And for the third position, you're going to subtract again since you already used 2, okay, 2 elements from the given set. So it will be n minus 2. And then next will be n minus 3 since you already used 3 characters from the first 3 elements or for the first 3 position. So that will be counting one-to-one function. You're going to remove one, or you're going to remove the use elements from the characters that will represent a certain position. Okay, so generally, to generalize that, the result will be n for the first position times n minus 1 for the second position, n minus 2 for the third position, times up to the last position, n minus m plus 1. Why m plus 1 here? Because on the first position, we start with 0. We're subtracting 0. So 0 to m. Okay, don't forget, when we start with 0, so it will be the last value on your range will be subtracted by 1. So m minus 1. Or here, it will be n minus m plus 1. Since you subtract all m to n, so you need to add 1 for the last element. Okay, so that will be our formula for counting one-to-one function in case there is a problem that limits you to use the used element, okay, from other position. Okay, so let's have this. The North American Number Plan, NANP, specified that a telephone number consists of 10 digits, consisting of 3 digits area code, a 3-digit office code, and 4-digit station code. So there are some restriction on the digit. So let X denote a digit from 0 to 9. Let N denote a digit from 2 to 9. Let Y denote a digit that is 0 or 1. Okay, so in the old plan, it is used in 1960s, the format was NYX and NXXXXX. But the current plan now, the format is NXX, NXX, XXXX. So we're going to determine the different possible telephone numbers from old and from new plan. Okay, so how we're going to do that? Okay, so we're going to use the product rule. Since we know the number of ways for n, number of ways for y, and number for ways for x, so just multiply it, then we have the number of ways in representing a telephone number in the North America. Okay, so let's answer. Okay, so let's define first NYX. So N is 2 to 9. So it means we have 8 possible ways. So it's 8 here times Y, which we only have 2 ways. So times 2, X, 0 to 9, we have 10 ways. So it means for the area code for the old, we have 8 times 2 times 10, which is equivalent to 160. So we have 160 area code for the old plan. And for the new plan, NXX, so it is 8 times 10 times 10. Again, N, we have 8 characters, 2 to 9. Then X, 10 characters. So that's why we have 8 times 10 times 10. We have 800 area codes for the new plan. Okay, and for office code, for the old, we have the NNX. So we have 8 times 8 times 10. We have 640 office code. Okay, and for the last 4 digits of, okay, for the old and new, so since we are representing one position using X, so it means we have 10 characters. So 10 times 10 times 10 times 10. So we have 10,000 station code for each area code. Okay, so getting the number of ways in representing telephone numbers in old plan. So we're just going to multiply the area code for the old 160 times the office code for the old 640 times the number of station code, which is 10,000. And the product is 1,024,000,000. So this is the number of telephone lines that could be used in the old plan. For the new plan, we have 804, the area code, times the office code, it's still 800, times the number of station code, which is 10,000. So the result is 6,400,000,000. Okay, so this is the number of telephone numbers that could be used in the new plan. So as you can see here, by changing the rule, we could have different answer. Okay, because we are changing the number of characters used in one position. Okay, so if you're going to increase the number of characters in one position, definitely the number of ways in representing that pattern will increase. But if you're going to limit the number of characters, okay, or we're going to lessen the number of characters in one position, it will lessen the number of patterns to represent that. Okay, so that's the effect of the number of characters. Okay, so that's why here in the Philippines for the telephone number, we increased the area code so that we could have more telephone numbers that could be used by the user, from 7 characters to 8 characters, even in our car plate, okay, vehicle plate. So we increase it from 6 to 7 to increase the number of possible ways for our car template or for our vehicle template. Okay, now, so product rule in terms of set. So basically, if you want to determine the number of ways, okay, if the given is a set or sets, so we're just going to determine the elements of each set. Okay, the cardinality of each set. So for example, a sub 1 times a sub 2 times a sub 2 a sub m. Okay, so if we want to get the number of possibility, so get all the set cardinality of each given set, okay, and then multiply it to determine the number of ways. Okay, so that is product rule in terms of set. And one application of product rule was used. One application of product rule is in determining our DNA or our RNA. So it helps um, the scientists to determine the DNA structure. So using product rule, using counting. Okay. So I'm just going to show you some of the details about DNA, RNA, and others. Okay. So now let's move on with the sum rule. So sum rule, if a task can be done either in one of n sub 1 ways or in one of n sub 2 ways, where none of the set of n sub 1 ways is the same as of the n sub 2 ways, then there are n sub 1 and n sub 2 ways to do the task. So basically in sum rule, we have, okay, we have different ways, but they are independent with each other. So if we have this, so we're just going to add the different ways. Okay. Okay, so we have n sub 1. We have different ways in representing n sub 1. We have n sub 2, different ways, and they are independent with each other. So we could add the number of ways, and we have the total number of ways for that problem. So that's sum rule. Okay, so for example, the mathematics department must choose either a student or a faculty member as a representative for a university committee. How many choices are there for this representative if there are 37 members of the mathematics faculty and 83 mathematics major and no one is both a faculty member and a student? Okay, so we're going to get a representative, and that representative could be either a student or faculty. Okay, so just only one, a faculty or a student. Okay, so if we have this problem, we could choose the sum rule. So what is the number of possibility? If it's a faculty, it's 37. The number of possibility, if it will be a student, we have 83. So just add 37 to 83, we have 120. So it means we have 120 possible ways to determine the representative of the mathematics department. Okay, 37 is independent with 83. 83 is independent with 37. Okay, since we have two distinct sets to represent a representative. Okay, so therefore we're just going to add all possibilities based on the given sets. So we have 120. So that's the sum rule. Okay, so sum rule can be used if and only if the given sets are disjoint. But in case if it's not, where you cannot choose the sum rule, but another rule will be implemented. Okay, so let's have this example. Suppose statement labels in a programming language can be either a single letter or a letter followed by a digit. Find the number of possible labels. So it could be one digit, one character, or two characters. If it is one character, it could be a letter. But if it's two characters, so it should be a letter followed by a digit. Okay, so we have two distinct groups, okay, to determine the label of the programming language. Okay, so how we're going to determine the possible labels. So first, the first option is the single letter. So how many single letters do we have? We have 26. Okay, so that will be the first option. So 26 character. So we have or, so plus the other group. So characters and digits. So letters for the first position, 26, followed by the 10 digits, multiply it, we have 260, plus 26, we have 286 ways. So again, 26 represents if the label is just a single letter or a single character. And if it's two characters, so this is how we label it, 26 times 10. Okay? Character and a number. And all possible ways, so we're just going to add single character with double character. And we have the all possible labels for your programming language. So we have 286 ways. Okay. Okay, counting password. So we're going to combine the sum and product rule to solve this complex problem. So each user on a computer has a password, which is 6 to 8 characters long, where each character is an uppercase letter or a digit. Each password must contain at least one digit. How many possible words are there? Okay, to solve this, okay, so we're going to have a separate solution for 6 characters long, 7 characters long, and 8 characters long. And don't forget, we have a limitation here. So it should be at least one digit in one password. So it means all letters for 6 letters is not, okay, it's not acceptable as a password for this example. Okay, so we need to remove it from from our ways in representing our password. Okay, so we're going to remove the all possibilities that it will be all letters. Okay, we're going to remove it from the universal ways. Okay, so the solution will be, so 36 raised to 6, so I 36 raised to 6. Okay, 26, okay, plus 26 characters from the English alphabet plus 10 characters from, okay, from the integer. So we have 36, y raised to 6, we have 6 position. 36 for the first, 36 for the second, 36 for the third, 36 for the fourth, 36 for the fifth, and 36 for the sixth position. Okay, and then we're going to subtract the possibility that all characters will be an alphabet. Okay, so there is a possibility that, okay, so it's 26 raised to 6. Okay, for the possibility that it will be all letters. Okay, so why 26 raised to 6? Because the first character, again, could be all possible letters. So we have 26 letters times 26 times 26, 26 times 26. Okay, so that will be the possible ways in representing our password. Will be represented. The password will be represented by all letters. Okay, 26 raised to 6. Okay, so we're going to remove it from all possibles, from 36 raised to 6, to get that 1,867,866,560. Okay, so again, we are removing 26 raised to 6 because this is the all possible ways in representing the password just using the letters. We're going to remove it from this 36 raised to 6. Okay, so the result is 1,867,866,560. Okay, and we're going to repeat this solution for password with 7 lengths and 8 length rather. Okay, so 36 raised to 7, again, we have 36 ways in representing one position, both letters and characters in English. Okay, minus the possibility that it will be all letters. So it will be 26 raised to 7, the possibility that it will be all letters. So again, 26 times 26 until for the last position. So we have 8 billion. Subtract it to 78 billion, we have this result. So just repeat the solution for 8 string bit. So we have 36 raised to 8 for all possible ways, okay, and minus all characters, okay, all possibility that it will be all English alphabet. So 26 raised to 8, subtract it to 36 raised to 8, and we have this result. And the result will be added to get the all possible ways for the password. Okay, so this will be the result. Okay, so that's why it's harder to determine the password if your the length is variable, okay, and if you have lots of characters, possible characters that could be used in one position of your password. Okay, so that will be counting password. And also we could use product rule and sum rule in determining the number of internet addresses. Okay, so using the same procedure, so if you have some restriction or some addresses that cannot be used in your internet address, so it's just subtract it from all possible ways to determine, okay, the internet address, okay, subtracting the subtracting the what do you call this, the restriction. Okay, and now in case there is a in case the given is not disjoint, the sets are not disjoint, so you're going to use subtraction rule. Okay, so if a task can be done either in one of n sub 1 ways or in 1 n sub 2 ways, then the total number of ways to do the task is n sub 1 plus n sub 2 minus the number of ways to do the tasks that are common to the different ways, also known as the principle of inclusion and exclusion. That's your subtraction rule. Why do we need to subtract the number of ways which are common to different ways? Kasi it is redundant. Okay? Kasi it's already part with A and B. So if you're going to add, so parang dalawang beses kasi siya nabilang. So that's why we need to remove one set from when we add n plus 1 and n sub 2. That's the reason of subtracting, okay? Subtracting the common. Kasi twice siyang nabilang. Okay? So let's discuss this counting bit string for some restriction. Okay, so we want to determine the all possible ways based on the given restriction. So first, how many bit strings of length of 8 either start with 1 bit or end with the 2-bit 00? Okay, so we have 3 possible pattern. It will just start with 1 or ends with 00, or it starts with 1 and ends with 00. So for counting bit string, we need to determine first all possible ways, okay, that it will start with 1. So disregarding the first bit, we have 7 bits. Okay, so it means, okay, so it means that, so possible ways for the first and second position is 2, 2, 2 until the last position. So just multiply, we have 2 raised to 7, we have 128 ways, okay, in ways in that it will start with 1, okay, but in case it will end with 00, so we only have 6 bits here, So it means we have 2 raised to 6 or 64 ways, okay, that it will end with 0, 0. And 4 start with end and ends with 0, 0. So removing the first digit and the last 2 digits, we only have 5 positions left. Okay, so 5 position. So it means we have 2 raised to 5. Okay, 2 times 2 times 2 times 2 times 2 number of ways, or 32 ways in, okay, or 32 ways pattern that the string start with 1 and end with 0, 0. Okay, so we're just going to add 128 plus 64. Since 1 and 0, 0 is already part of the pattern that that starts with 1 and that ends with 0, 0. So it means these two, okay, are not disjoint. So therefore, we're going to subtract 32 from the sum of 128 and 64 to get the final way. So we have 160. Okay. Okay. So that will be the counting bit string. Okay, using the subtraction rule. So again, we subtract 32 ways because it has already been it is part of the first, okay, the first pattern that starts with 1 and the second pattern that starts with that ends with 0, 0. So it means that some pattern in the first and some pattern in second, okay, can be they shared, and there are some patterns that can be found on the first and then the second row. Okay, so again, if we have that, you could use subtraction rule. Okay, so you're just going to find the number of ways, okay, which is common between the two given rules. So that's counting bit string. So for the next video lecture, we're going to discuss pigeonhole principle. So this will be my last slide for this session. So if you have any questions, kindly send me a course message, please. Thank you.